I think it should be recording now.
Mm-hmm.
I'm also recording, but just in case.
Hi, Farah.
Let's see, should we go ahead and get started?
Sure.
So today we're very happy to have Matty Seiberg, and his talk title is Continuum Quantum Field Theories for Fractons.
Thank you for the invitation. This talk will have some overlap with similar talks I gave with the same title and very similar abstract. And some people who attended before, I apologize about the overlap, but I think that the emphasis here will be a little bit different than in previous talks, where I emphasize more the continuum quantum field theory that is being discussed, and I will mention the underlying lattice systems only very briefly. So that would be the main difference, because I think that these systems are interesting, as I will outline soon, even just as pure continuum quantum field theory without ever mentioning the underlying lattice system that motivated them. So I'll be talking about 4 recent papers, and there are a few other papers kind of follow up on that I'm currently writing with various collaborators. The bulk of the talk will focus on this paper, but I will also mention the content of the other papers. So let me start with a general introduction. We have a standard law that has been extremely effective for several decades, that if we start at short distances with some lattice system, with local interactions, the low energy limit can be described by continuum quantum field theory. And this has been extremely powerful, both as an organizing principle of the short distance, of the long distance behavior, the allowed phases of a system, but it's also effective in the sense that it captures the universal aspects of the system, which do not rely on the various short distance contamination that can happen. So various different lattice systems with different lattice interactions and so forth give us essentially the same long distance behavior, which is characterized by a small number of coefficients, a small number of parameters, and most of the information about the short distance theory is strictly irrelevant. So this is both a very powerful tool, it's a very good organizing principle, and until recently there was no doubt that this is really the way things work. But over the last few years, and it's really only a few years, some examples of lattice models came out. Some of them have fractons, some of them don't. I'll mention that later. And they are clearly counterexamples to this law in the sense that they do not fit this framework. In other words, we're going to start from an innocent-looking lattice system. We can start from an innocent-looking quantum system with local interactions. Everything looks sensible. But by the time we examine the system at long distances, we see that it cannot be captured by standard continuum quantum field theory. So this raises a big question about the validity of this law. Is this law really right? So in addition to the fact that these models are extremely interesting on its own right, I would like to focus on this aspect. To what extent can we always capture the long distance behavior by a continuum quantum field theory? And since there's this apparent contradiction that I will soon elaborate on, it's clear that we'll need to expand the framework of continuum quantum field theory to accommodate these models. But on the other hand, quantum field theory is a very tight structure, and it's not easy to extend the framework without wrecking the whole structure. So we would like to extend it as little as possible, and in fact, the extension that I will be describing will be essentially unavoidable. Now, it might very well be that trying to fit these systems into the framework of continuum quantum field theory is a misguided effort, but I think it's clearly worth doing it because of two motivations. Number one, related to what I said here, we would like to have a better organizing principle for these systems, see what are the different behaviors that are possible, how we should think about them, and give them a universal description. And the second thing, which might be more of an interest to this audience, is that maybe it will teach us something new about quantum field theory. So let me say a few words about fractons. There are many different examples, and they all have different characteristics. And there's every reason to believe that there are many more examples that have not yet been found and should be found. And some of their characteristics, so it's very hard to put the characteristic on one slide, and definitely not in 3 bullet points like here, but let me try and do that anyway, allowing me some error bar here. The first thing is that there are particles of restricted mobility. So the spectrum includes particles which are either restricted to be at a point, or restricted to move on a line, or restricted to move on a plane. So a particle that can only move in the XY plane, but cannot move in the Z direction, and another particle that can move only along the X direction, but cannot move in Y and Z, and there are particles that cannot move at all. And I emphasize that these particles that cannot move, it's not just that we'd have to give a lot of energy in order to move them. If we give them a kick, they don't move. They can't split to other particles, but as a single particle, they cannot move. So that's what I mean here. That's already looks strange. The second point looks even stranger. In the gap systems, there's a there's a ground state degeneracy. So and it is such that it is infinite in the continuum limit. So let me define what I mean by the continuum limit. Here, most condensed matter people take a different limit of the system. They have a fixed lattice size, and they take Li, the number of lattice sites in the I direction. They take it to infinity, but we would like to take true continuum limit with finite volume. So L is the length of the system. We're going to take the lattice spacing to 0 and Li to infinity with fixed length. So again, we'll be working on a rectangular square lattice, say in 3 dimensions or in 2 dimensions. So this would be space. And we have Lx sites in the X direction, Ly sites in the Y direction, and Lz sites in the Z direction. And then we'll try to take this continuum limit, scaling these lengths to infinity, holding the physical system of fixed size. And these systems are solvable, and they are gapped. So here I limit myself to the gapped cases. And in a gapped phase, normally we have one ground state, or maybe a finite number of ground states. If this is a topological field theory, it has a finite number of ground states. But the surprise here is that the number of ground states grows with the number of lattice sites. So if you add one more layer of sites to the underlying lattice, the number of ground states grows very fast. I also emphasize that it is actually infinite in the continuum limit. So if we're going to have a continuum field theory description of that, it is unavoidable that we will end up with a system that has an infinite number of ground states. Now, we know systems that have an infinite number of ground states, like we have independent degrees of freedom at different points in space. I emphasize that this grows only like the length of the system, not like the volume. So this is already very strange, because being a long distance person, I can count the number of states. And by counting the number of states, I'm sensitive to some lattice information that is very strange, because normally the long distance behavior is independent of most of the lattice information. This is a particular aspect of it, that the system has exotic global symmetries. And these are symmetries that, like high form global symmetries, are integrated only on a subspace of space. They're also called subsystem symmetries. But the value of the charge is different at different position in space. So if I say integrate on the XY plane, and I move this plane in the Z direction, for different values of z, the charge can have a totally different value, 1, 2, 7, etc. Which is again very peculiar. Because you're used to charges either being independent of the position or operators that vary smoothly as we change the operators. Here, they're completely erratic. They can jump from point to point. So all this tells us that the ground states reflect short distance physics. If we just look at low energies and even just the ground states, they're sensitive to what happens at the lattice scale. They are sensitive to the orientation of the lattice. They're sensitive to the number of sites in the lattice. And expectation values of operators have high momentum, even though we're at low energies. In other words, if I move the operator, say, as I said before, in the z direction, it can have different values. The charge can have different values at different values of z. And that means that it has high momentum in the z direction, even though we are at low energies. Now, all these features, if we just look at them, are essentially impossible in a standard continuum quantum field theory. They seem to contradict the renormalization group picture. So we'll have to expand this feature, expand the standard framework of continuum quantum field theory. And we are really walking on very thin ice here because the structure that we're dealing with is very tight. And as the structure is very tight, we start making changes. We allow things that are normally not allowed, and I will do that soon. Everything has to be rethought because we might be getting into a contradiction. So let me first say what the punchline will be, what the new elements will be. So we will present some continuum quantum field theories, and they will go outside the regular framework of continuum quantum field theory. But I would like to emphasize that wherever we are going beyond the regular framework, it is essentially unavoidable. So there will be two options. Either this kind of system should not be forced into a framework that looks like quantum field theory, or it is essentially what we're saying, because no other option is available. So the first ingredient is not that shocking. We're going to have translation symmetry, but we're not going to have Lorentz invariance. This is completely standard. The non-Lorentz invariant continuum quantum field theories have been studied for decades. We are also not going to have rotation symmetry. We're only going to preserve rotations by 90 degrees. So if we are in 2+1 dimensions, the spatial group is Z4. If we are in 3+1 dimension, the spatial rotation group is S4, which is the rotation group of the cube. We can also add parity and time reversal, etc., but we're not going to have continuous rotations. And not only will the Lagrangian violate the symmetry, in some cases, we'll also study fields that are a non-trivial representation of, say, the cubic group, rather than being a complete representation of SO3. This is quite palatable. It might be disturbing, it might be unusual, but things like that exist in the literature. That's not very surprising. The second element, which is a little bit more surprising, is it will have various exotic symmetries. I'll explain them later. And then we'll study gauging these exotic symmetries. And these exotic symmetries will have the feature that I mentioned before, that as we move the charge in space, the value of the charge can change discontinuously. In fact, we'll have various delta functions and things that jump around. Perhaps the most dramatic thing that we will contemplate is considering discontinuous fields. And we're not experts in analysis, and we must have we might have not been careful enough, but I feel that this is essentially unavoidable. In fact, if we would like to present a system that has these charges that vary discontinuously, we must allow discontinuous fields. So I should clarify that the fields will not be as discontinuous on a lattice. On the lattice, everything is discontinuous because the fields at different points are totally uncorrelated. But they will also not be as smooth as in the standard continuum field theory. And we will consider maps from space, which is space-time, which is continuous, and the map to target space will allow certain discontinuities, and I'll spell out exactly what we allow and what we do not allow. Since we will also consider gauge theories, we'll have to say what we say about the gauge parameters. And if the fields we study can have various discontinuities, the gauge parameters and the corresponding transition functions can also be discontinuous. So we will discuss situations where we cover our space with patches, and the transition function from one patch to another is a gauge parameter, and the gauge parameter will have its own periodicity, that's standard, but we will also allow certain discontinuities, and they will be essential in what we will be saying. And the last thing that we should emphasize is whatever we do, we'll insist that what we do is universal in the sense that it's not sensitive to the details of the underlying lattice system. So these are the principles. If you don't like them, this is the time to leave, because now I'm just going to elaborate on them.
Howdy, hi, this is Thomas. Instead of leaving, can I ask a question?
Yeah. So it reminds me of the famous Groucho Marx line. These are my principles. If you don't like them, I have others.
Right. I wanted to ask a quick question about the breaking of Lorentz and rotation symmetry. So the lattice models that you consider, they break them at the high scale. But you could imagine a UV-complete Lorentz invariant field theory that you then put on a torus, and that where all of this behavior is in principle emergent. Is that somehow impossible?
I don't think it's impossible, but this would be a much more sophisticated thing to contemplate. For the moment, I give up on this symmetry, so I would not like to get the fact that I gave up on the symmetry. I wouldn't like to get that dynamically. I would just like to, let's explore what we can do without having that symmetry.
I guess I was asking whether it's obvious that it cannot happen in the other context.
Well, I cannot prove that something that I didn't try that cannot possibly happen. It might be that somebody will generate these systems out of some dynamical condensation of something or another. That's logically possible.
Thank you.
I don't think it will be easy though. And to be honest, I see other issues which are much more urgent than this one. But it's worth exploring. So, for example, if you would like to get this structure out of string theory, as some people suggested, then we'll have various stacks of the branes at an angle and this and that. That's an issue that one will have to contemplate, namely how to get this lack of symmetry out of a system which does have that symmetry. Did I answer your question, Thomas?
Yeah.
Good. So before jumping into the details, let me put here a qualification, as my lawyer forced me to put it in. So we don't have a general systematic presentation. I've already mentioned that, and I'm giving the end list of gaps that I feel should be closed, perhaps by people who are more mathematically powerful than I am and knowledgeable than I am. Our understanding is incomplete. And the way we worked was to take concrete, explicit lattice models that were studied with a lot of detail by the condensed matter people. So these are systems that exist. They analyze them analytically, they analyze them numerically, they analyze them with all sorts of techniques, and we just tried to fit them into the framework of quantum field theory. By the time we finished writing these papers, I counted that we studied 11 different continuum models. Some of them turned out to be dual to each other, so there ended up being only 6 distinct models. By now, with my various collaborators, we've analyzed many more. We had at least doubled the number of systems that we studied. And they do have some common features, and as we go to more and more sophisticated models, there are new features. But I would like to start here with the simplest of them and analyze it in some detail, and then I'll mention what happens in more sophisticated cases. So I'm going to start with the system in 2+1 dimensions, and it was first introduced by these 3 gentlemen. These are condensed matter people, and the system was analyzed in various cousins of this system were analyzed by a lot of people by various techniques. But here I'm going to jump directly to the lattice, to the continuum version of this system. Namely, we have a lattice system. There's a clear recipe how to go to weak coupling, perform the small fluctuations, and find a continuum Lagrangian. So I'm going to write a continuum Lagrangian and forget where it came from and just analyze the continuum Lagrangian. And that's a Lagrangian. So this Lagrangian looks rather innocent in the continuum. I'm suppressing coefficient. There's a kinetic term here. And there's a spatial derivative term. There's no d by dx phi square. There's no d by dy phi square. There are also no other terms that could be added. I'm just taking this Lagrangian as is, where phi is circle value. So phi is a compact scalar field, and this is our Lagrangian. And since it's free, we should just analyze it. We open the textbook and we just analyze what this system does. And as you will soon see, despite looking so innocent, it has very interesting structure. And I emphasize, this is a solvable system because it's quadratic. So what's the equation of motion? So the first thing we do is look at the equation of motion. We take the variation with respect to phi. This is the equation of motion. And we substitute a plane wave solution. And we find the dispersion relation. So far, it's completely standard. So it's not rotation invariant, and it's not, so definitely not Lorentz invariant, but this is the dispersion relation. And here we see the first peculiarity, which is really the key fact that triggers most of the other subtleties we'll discuss later, that if we set Py to 0, no matter how large Px is, the energy omega is 0, and vice versa. So as long as Px and Py are generic, the dispersion relation is non-standard, but things work essentially the same as in the standard free scalar field theory. But here, because of the peculiar dispersion relation, the region here, Py equals 0, and if we go specifically exactly to Py equals 0, being at low energies does not mean low momentum, because if Py equals 0, Px could be arbitrarily large, and the mode still has a 0 energy. And this will have important consequences. It's very reminiscent to a phenomenon that had appeared earlier in string theory in various contexts, especially in non-commutative geometry, of UVIR mixing, where long distance behavior is sensitive to the high momentum behavior of something else. So large Px can affect us at low energies, and we'll soon see the consequences of that. So this is the dispersion relation. And again, this is the equation of motion, and it's a free theory, so we'll continue to analyze it. And we can interpret it as the conservation of a net of current. We just give d0 phi a name, and we give dx dy phi a name, so we have these derivatives. And this looks like a very strange conservation equation, and it's strange because we have two derivatives here rather than one derivative. And since we have two derivatives here, the conserved charges, the conserved network charges, are q sub x, which can be a function of x, and q sub y, which can be a function of y, obtained by integrating this current only over y or only over x. Emphasize again, I work on the torus with periodic boundary conditions, and the torus is in the x and y directions. And notice that these two charges are conserved, because if I hit it by d by dt, I use the conservation equation here, and then I can do the y, I can integrate by parts dy, and I get 0. And on the other hand, this charge, q sub x, does depend on x. There's no reason it shouldn't depend on x.
Nati,
So, yeah.
It's your definition of the current. You could have moved derivatives here.
Yes, I could have, but it turns out that you do not get more information than what I've presented here. And I can say more about why it happened later. In fact, I might or might not get to it. This operator is well defined. If I write that as d by dx square times the current d by dy square of phi, that will not be well defined. But at the very least, I can tell you that by organizing the derivative differently, you're not going to get more information about the conserved charges. So yes, you could have tried that, but it will not give more information. And I also emphasize that the 0 mode is shared, because if I integrate both over x and over y, it's clearly the same thing. So the 0 mode is shared. So we refer to the symmetry as a momentum symmetry, and I'd like to emphasize that this is momentum in the target space rather than momentum in the coordinate space. Momentum in the coordinate space is what we called earlier P sub x or P sub y, etc. But this is very similar to what we do in a free field theory, where we have a momentum symmetry that shifts phi by a constant. And we'll call it entitled symmetry for reasons that are not obvious from this presentation, essentially because we have two derivatives in the conservation equation. So once we have the charges, we can act on the fields that commute Q with the phi and see how the symmetry acts on the fields. And we see that it shifts phi by arbitrary function of x plus an arbitrary function of y. So the Q sub x shifts by an arbitrary function of x, and Q sub y shifts by an arbitrary function of y. And you can check, this is a straightforward exercise, that this shift symmetry is indeed the symmetry of this Lagrangian. So this is kind of a sanity check that we didn't fool ourselves. If you ask yourself, what are the global symmetries of this system? An infinite symmetry, an infinite symmetry. Now there's an important subtlety that we said that phi is circle valued. Now, alpha of x, let me step back a little bit. I've said it here, but I would like to emphasize it. Alpha of x and alpha of y, these two functions, can be discontinuous. Normally in field theory, we do not consider discontinuous functions, but this is the first time in this analysis that we see that discontinuous functions raise their head. And the reason this is harmless to have these discontinuous functions here, because the Lagrangian doesn't change. So if we shift phi by a discontinuous function of x, this thing is still finite. In fact, it's still zero, it doesn't shift, because d by dx might be infinite, but the d by dy kills it. Okay, so now that we have discontinuous function of x here and a discontinuous function of y here, we could ask, what does the periodicity of phi mean? It means that we should identify configurations that differ by 2 pi shift. But if phi can be discontinuous, phi can have certain discontinuities, we must identify 2 phi's that differ by 2 pi times an integer valued function of x plus an integer valued function of y. So these are clearly discontinuous functions because they are integer values. So 2 phi configurations that differ by 2 pi shifts in x, or 2 pi shift for every value of y, as a function of y, are identified. And that means that the shift momentum symmetry, this alpha of x and alpha of y, are at every point x and y are circle value. So the symmetry is U1 rather than R. Let's go back to the spectrum of the theory. We discussed the dispersion relation. And for generic Px and generic Py, this is completely straightforward. We look at these modes. We have creation and annihilation operators. We have a Fock space of states. The only thing which is non-standard is that the energy of each creation operator, the energy carried by each creation operator, is a non-standard function of Px and Py, but other than that, things are normal. But the peculiarities are, of course, associated with the modes with 0 omega. These are modes with either vanishing Px or with vanishing Py, and they need special attention. What does it mean to have vanishing Px? It means that the mode is independent of y. Vanishing Px, it means it's independent of x. And vanishing Py means that it's independent of y. So if we write phi, our arbitrary function in the functional area, is phi 0, which is completely continuous, plus a discontinuous function of x and a discontinuous function of y, the modes with either Px or Py equal 0 are these modes. And indeed, if we take such a configuration of phi, even though these are discontinuous and we substitute that in the action, we get finite answer. Normally we say that the reason we would like continuous functions in quantum field theory is that we would like the action to be finite. Here we can have finite action even with discontinuous fields. So the argument that fields have to be continuous, this argument evaporates, and indeed we see that the system can have discontinuous functions. Now we can think of these modes as being associated with a spontaneous breaking of the momentum symmetry. We said that there's a symmetry shifting phi by a function of x plus a function of y, arbitrary function of x, arbitrary function of y. And when we try to quantize the effect of these modes, so we say it's not an arbitrary, it's an arbitrary function of x, but it can be time dependent, or an arbitrary function of y, and it can be time dependent. So that looks like these modes of phi can be thought of as the Goldstone modes associated with the spontaneous breaking of that momentum symmetry I mentioned earlier. However, we'll soon see that this is not the case. So what do? We take this system and we would like to quantize these modes more carefully. So let's quantize the modes with py equals 0. So we just have to substitute this in the action. And because of the zero modes of the two modes are tied together, a little bit more care is needed, but that's done in the paper. I'm not going to do it here. So if I substitute this in the action, this is the Lagrangian. Substituting the Lagrangian, that's what I had. This function f, this is the time derivative term. The dx dy pi squared term drops out because this depends only on x. And that's the problem we have to solve. So at every point in x, we have a separate coordinate f of x, which can have time dependent, and it is separately 2 pi periodic. So if we look at one value of x, what we have is a quantum mechanical system of a rotor, a particle that lives on a circle. But there's an interesting subtlety here, that here we have an integral. We don't have a finite number of modes, we have an integral. So if we try to think of it as a finite number of modes, imagine we discretize the integral x, we get a sum over all positions, we have this integral, but now we have another factor of the lattice spacing out front. So when we write the system, we tentatively regularize it on the one-dimensional lattice, we have an infinite number of rotors, 1 per x, but the coefficient in front of the rotor, it goes to 0 in the continuum limit. What this means is that when we quantize this quantum mechanics, imagine A were finite, then the energy of this mode will go to the momentum. There is a momentum conjugate to F, and it's an integer, separate momentum at different values of X, and the coefficient here is inverted. There are factors of 2 that I'm not paying attention to. And this is the energy of the system. We just go over the rotor. Each rotor has energy, has momentum, which is an integer, and the coefficient here is infinite. The fact that the coefficient here is infinite means that all these momentum modes that would have been the Goldstone modes of the broken global symmetry, not only aren't they there, they actually get infinite energy. So this is the infinite energy. In the continuum limit, all these modes are gone. So the global symmetry, which appeared like it was spontaneously broken in the classical theory, it's actually restored in the quantum theory. This is very similar. This is already true for the 1 + 1 dimensional boson in the 1 + 1 dimensional compact boson. There's a momentum symmetry which appears to be spontaneously broken classically, but the symmetry is actually restored in the quantum theory. So how should we think of these modes? How should we interpret them? The conservative approach would say that these modes have infinite energy, and if they have infinite energy, we should just forget about them. So there were modes that appear to be soft. These are these funny modes that give us UVIR mixing, but when we quantize them and we take the continuum limit carefully, they get infinite energy and they're out of the spectrum, and therefore we shouldn't discuss them. A more interesting and more ambitious approach is to say that these states carry charge, and they are the lowest energy states of a given charge. So the continuum Lagrangian does capture them correctly, and these states and small fluctuations around them are described correctly by our continuum Lagrangian. And in fact, we can verify that by going to a lattice system of the whole thing where everything is finite, nothing is ever infinite. This A is finite, is not 0. And there we see that the continuum Lagrangian does indeed capture the correct answer. So this is the momentum symmetry. This system also has a winding symmetry. We already discussed the momentum symmetry in its conservation equation. So this was a Netter equation, and these are the currents. And Shimon asked me whether I could reshuffle the derivatives, but I didn't. But just as we have this, we also have this equation. We can let d by d0 act on this operator and dx dy act on that, and that's like a winding symmetry. And the conservation equation looks the same, except that jx, y, and j0 are constructed differently under the microscopic fields, but other than that, it's the same equation. And therefore, we have the same global symmetries. An integral over y at fixed x, or an integral over x at fixed y, and the 0 modes are tied together. We'll refer to that as winding symmetries. So what are the charge states? We need to find a configuration, classical configuration, which is a function of x and y, independent of t. That would be the winding mode. So in string theory, we're familiar with that. We are in 1 + 1 dimension, and we have phi that grows linearly in x with an integer coefficient. Here we can do things that are a little bit more interesting and have these discontinuous functions. And if I just look at this thing, everything, both x and y and x0 and y0 are in the fundamental domain of the torus besides Lx and Ly. And you can check that this phi is a periodic configuration on the torus. More precisely, phi is not periodic, but e to the I phi is periodic. Because if we shift x by Lx or y by Ly, the function is shifted by a Heaviside theta function. This theta is the Heaviside theta function. So this is an interesting configuration to study. And if we just substitute it into the winding symmetry charge, we find that we have delta function charge localized at x0 and the delta function charge localized at y0. Now, what should we make out of the symmetry of these charges? It's a little bit strange because the action of this configuration is actually infinite. And I made a big deal earlier that we should study discontinuous functions, but only insofar as their action is finite. The action of this configuration is infinite, but if we substitute this in the action, the double derivatives gives us a delta function. And when we square it, we get delta of 0, so it's infinite. And if we regularize it somehow, it's at order 1 over A. So the energy of the winding states is infinite. And again, mirroring the two options we had with the momentum charges, momentum states, we have two options for the winding states. The more conservative approach states that these configurations have very high energy, in fact, infinite, and therefore we should discard them out of in the continuum theory. We shouldn't study them at all, and that's it, forget about it. And the more interesting, the more ambitious approach states that these configurations are the lowest energy configurations that carry some charge, and as such, that they are interesting. And the continuum theory captures the physics of these winding configurations and small fluctuations around them correctly. And again, we can go back to the lattice, repeat the whole computation on the lattice, and realize that the continuum theory was clever enough to reproduce the correct answer without ever mentioning the underlying lattice. Now, this whole thing starts sounding very familiar. We have...
Nani, you're going to tell us, but could you summarize now? It would be helpful. What are these universal properties? Because the energy is infinite.
The energy is infinite, but if you look at
I don't know what it means for an infinite energy to be universal, but there are other properties that are going to be...
The other properties, like, for example, the spectrum of small fluctuations around it, the Fock space states, et cetera, et cetera. And the main difference, if you relate...
So is it like a defect where the energy is infinite, but there's a spectrum, there's a Hamiltonian in the...
That would be
Hamiltonian in the presence of the defect?
It's similar, except that a defect is something that you put on the system from outside. Whereas here, this does appear like an excitation of the system. A defect would be that I draw a line in space and I say that at all times, and I say that here we have some boundary conditions. Right? That's what the defect does. So it's not something that this is something that I can add from the outside to the theory, and it does not carry a conserved charge. This object does carry a conserved charge. So it's more like a dynamical excitation in the system. Admittedly, it's a dynamical excitation with a lot of energy. But so if A is small but not 0, there's an operator in the spectrum that creates this guy.
So what's the difference from a 't Hooft line, which is which does carry a conserved charge, and we can think of, you know, as a system with a very heavy particle, which is...
Because the properties of this guy are universal. They came out of the... Yeah, it's similar, but I'll have to think of a better answer. But it's clearly different because it came out of these configurations that are infinite, that are within the quantum theory. Okay, let me give you a slightly more technical answer. If you put the system on the lattice, then the 't Hooft charge means that F is a delta function on the lattice, and that delta function on the lattice is at the scale of the lattice spacing. So if I write the system on the lattice and there are Links variables and Plaquette variables, the Plaquette variable is the phase of the Plaquette variable is of order 1 rather than of order A square. So in all the continuum, the low energy states, the Plaquette variable is of order A square, and in the 't Hooft line, it is of order 1. This is in between, it's order A, not order A square. in that sense, it is more in the continuum theory than the defect line, rather than like the monopole of the lattice theory. I can explain it in more detail.
Okay, thank you.
But very soon we'll get examples where we'll get exactly the same functions and the energy will be of order 1, and therefore I will have no choice but to study the to take the ambitious approach.
Can I also just ask another
At
quick
this
question?
point, it looks like I have an option. Which of the two I take? You will soon have other examples where exactly this configuration will appear, and I will not take the option. And then it will be clear that it's not like the total. So
Just one more quick question about the symmetry. So you said that we should take this seriously because it's the lightest charged state. But in order for that to be true, I need to be convinced that the symmetry is actually, true symmetry of the microscopic theory.
An interesting question. So if you formulate the problem on a lattice, the momentum symmetry is there on the lattice, but the winding symmetry is not on the lattice. So you could say, what are you talking about? It's like the XY model. It has momentum symmetry, but no winding symmetry. But if you look carefully at the lattice system, the winding symmetry is this winding symmetry is violated at energies of order 1 over a squared. So we don't take a to 0, but we make a very small. So we have very low energies. We have the continuum modes that are not controversial. At order 1 over a squared, we have all sorts of lattice modes. Also at order 1 over a, we have various lattice modes, but they are not charged under the symmetry. But the violation of the symmetry on the lattice is at order 1 over a squared rather than at order 1 over a. So I'm kind of this thing barely manages to make sense.
Are you saying that the conservation equation of your current, of your winding current on the lattice would have an a squared on the right-hand side?
Roughly speaking, yeah. The current is not conserved, but the configuration that violates it, so why isn't the lattice, the winding conserved? Because you have spins that rotate gradually, right? This is how you get winding.
Right.
But on the lattice, a spin can change drastically, can jump, and therefore we cannot say by how much things wind around. And so you can check how much energy or how much action it costs for the spin to change like that. And the key point here is that the action has double derivative. So the violation of the charge is at order 1 over a squared, whereas the energy of this guy is at order 1 over a. So in that sense, the lattice, if you look at the lattice excitations at order 1 over a, there is an exact symmetry, which is the winding symmetry. You have to probe the spectrum at order 1 over a squared, which is much higher energy, in order to see that the symmetry is not there.
Thank you.
So we can summarize this whole thing, and if you didn't like the answer, so it looks like you're not comfortable with the winding symmetry, but you're perfectly comfortable with the momentum symmetry, which is a symmetry there on the lattice. But the two statements are actually too dual to each other. We can take the same scalar field and dualize it to a field phi tilde using similar standard formulas, and it maps the Lagrangian to itself, it maps the spectrum to itself, and it swaps the momentum modes and the winding modes. The momentum modes got energy of order 1 over a in the quantum theory, but they had 0 energy in the classical theory. The winding modes had energy of order 1 over a already in the classical theory, but this is exactly what happens in ordinary T-duality, where the energy of the momentum modes is 0 classically, and it's non-zero quantum mechanically, and the winding modes are non-zero, their energy is non-zero in the classical theory. And the only difference is that we are in 2+1 dimensions rather than in 1+1 dimension. And the second difference is that all these states have energy of order 1 over a rather than order a1. So this whole thing is very reminiscent to a compact boson in 1+1 dimensions. And as I said, there's T-duality that exchanges them. So this is the matter system. Let me rush now to the gauge theory. We'd like to make a gauge theory out of that. So what we're going to do is take the global momentum symmetry we discussed before and turn it into a gauge symmetry, gauge that global symmetry. So we had a conservation equation, and if we have a conservation equation, we can couple J0 and JXY to two gauge fields, and there would be an A0 for this and AXY for that. And this is how the gauge symmetry acts. So I read off the transformation laws using the conservation equation, the net current. And that's what we're going to study. So we have gauge fields A0 and AXY with these gauge transformations. And we'll just follow our nose and do what we normally do in such theories. So we can construct a gauge invariant electric field, and you can check that the gauge parameter, gauge variation from here cancels the gauge variation from here. And we are in 2 + 1 dimensions, so there's no magnetic field. The same problem in 3 + 1 dimensions does have a magnetic field, but this problem in 2 + 1 dimension does not have a magnetic field. We could ask, is there flux quantization? Is the gauge group U1 or is the gauge group R? So I've already discussed it before, and I said that alpha, the gauge parameter here, is subject to the same identifications as the phi I had before. And phi I had before was circle valued, and the fact that it was circle valued told us that because of this business with the discontinuities in X and Y, we should identify the gauge parameter alpha by alpha shifted by an integer X-dependent function here and an integer Y-dependent function here. And you can check that this is compatible with the gauge transformations. So now I'm declaring what the space of fields are, or at least first what I mean by these bundles, which would be very funny. The gauge transformation are alphas. Alphas can be discontinuous functions of X plus discontinuous function of Y. And this is the identification that we allow. And if we allow such identifications, we can study alphas that have that form. And this is a good transformation on our 2-dimensional torus. This is exactly the same function I had before. I'm not declaring what the Lagrangian is. I'm not asking about action of configurations. I'm only studying the space of fields we study. And in the space of fields we study, we should study the effect of such gauge transformations that are discontinuous in X and Y. So now we can construct a non-trivial bundle. I'm not sure the word bundle is right. I'm not sure what the geometry is, but I'll just copy words that are used in ordinary gauge theories. So I'm considering the system in a Euclidean box, and there are transition functions around the Euclidean time. So as I go around the time direction, I perform a gauge transformation. There's a transition function, which is this function, the same function I love and the same function I had before. And just by knowing the transition function, we can compute the flux. We can compute the integral of E. And because E is given by derivatives of the gauge fields, and so we integrate by parts of the derivative of the gauge field, and we read off the boundary terms using the transition function. So this is we just do the same thing that is often done, and we get a delta function of X and a delta function of Y, where the coefficients here are quantized. You see that the fields will necessarily will have delta functions in them, because if the integral has a delta function, then the field itself will also have some singularities. So what is the Lagrangian? So we're going to write an E square, and since we had that quantized flux, we can also write a theta term with a periodic theta. And now we can just follow our nose and do what we normally do. So we choose a gauge, A0 equals 0. Gauss' law tells us that dx dy of E is 0. And that can be solved up to a gauge transformation by such an AXY. So AXY is a function of X plus a function of Y with convenient normalizations. And the first thing we learn is that there are no local excitations. If we pick A0 equals 0 gauge, the solutions of Gauss' law, the solution of AXY modulo of gauge transformations is a function of X plus a function of Y, but there is no function of X and Y. So there are no local excitations. In fact, the whole situation is very similar to ordinary electrodynamics, U1 gauge theory, in 1 + 1 dimensions. Notice that our phi system was similar to a compact boson in 1 + 1 dimension. Now we see that this gauge theory is similar to U1 gauge theory in 1 dimension less. It is similar in the sense that there is electric field squared, there is no magnetic field, there is E with quantized flux, and there is a theta parameter. And there are no local excitations. In 1 + 1 dimensional U1 gauge theory, here it's only the holonomy, and here we have what you can quote in quotation marks, the holonomy in X and the holonomy in Y, which can depend on Y and X respectively, but no local excitations. Let's work out the spectrum of this system. So we just take this function A and we substitute it in the Lagrangian. And again, we ignore the common zero modes. This was done more carefully in the paper. And this is our effective Lagrangian. It's very similar to what we had before. We have decoupled systems at different values of X, right? We have decoupled systems at different values of X. And they again look like a rotor with a theta parameter. Everything is finite so far, except that there's one crucial difference between the same system we discussed before and this one, that if we look at the gauge transformation alpha I mentioned earlier, and it shows that this f is circle valued, but it's circle valued with a delta function. So f is the same as f plus 2 pi times a delta function. So there's an infinity here. So this is a rotor with infinite radius. Before we had an infinite number of rotors of finite radius. Now we have an infinite number of rotors with infinite radius. This means that if we put it on a lattice, we put this thing on the lattice, the A will not appear in the numerator, but the A will appear in the denominator. So when the dust settles, the spectrum of this theory is at every point X, we have an integer, and then there's a shift by theta over 2 pi coming from this term. And the coefficient of the energy is A. Before we had 1 over A, now we have A. So in the continuum limit, the spectrum is the following. There are no local excitations, but there's an infinite number of states at each X and an infinite number of states at each Y. So it's exactly the opposite of what we had before. Before, we had all these states and we could negotiate, do we take them seriously or not, and is it universal or not? Here, these states are there at low energy, in fact, at zero energy. We have an infinite degeneracy of zero energy states in a quantum theory. So this is the precursor of this thing that I mentioned earlier about the large vacuum degeneracy of fractons. We'll soon see that more explicitly. But the large vacuum degeneracy of the fractons, this is a precursor of it. Quanta is a quantum system, and when we are careful about what's periodic, is the periodicity infinite or zero, and how many states we have, and this and that, we have an infinite number of states. Let me study the defects of this system. We don't have any charged excitations, but we do have defects. The simplest one is just a particle moving in time. We have an A0, but remember there's no AX or AY. So this particle cannot move. It's a fractal. We can also study two particles with opposite charges, one at x1 and one at x2. Here we can use AXY to let this dipole move in the y direction. So a single particle, this is a proparticle, a single proparticle sits at the point in x and y, and it cannot move. And a dipole separated in x can move in the y direction, but not in the x direction. So it cannot move in this direction, it can only move in that direction. So this is called Linon in the condensed matter literature. Here we get the restricted mobility from the gauge symmetry of the problem. So
Nadi, the fractons are not actually excitations of the gauge field. There's some, this is what would, this theory of gauge fields would couple to fractons. Is that
exactly?
The
exactly. So the fractons, so what we have here is a low energy field theory that if at high energy we have charged particles that couple to it, there will be fractals. If at high energies we don't have these charged particles, then we could introduce these fractons as defect. Let me give you an example. The toric code in 2+1 dimensions has excitations with electric and magnetic charges, and they have braiding and this and that. And the low energy person would say the toric code is a Z2 gauge theory. The Z2 pure gauge theory in the continuum does not have electric and magnetic charges. Instead, it has defects, and the defects capture the effect of probe electric and magnetic charges. So the situation is very similar to that. We think of a system that has at short distances, perhaps electric and magnetic charges, etc., etc. The system is very complicated at short distances. We are trying to find a continuum description at low energies, a continuum description that captures only the universal behavior at low energies. And at low energies, there are no charged particles. But the low energy observer knows how to describe the effect of would-be massive charged particles as the effect of defects. So it's very similar to what is done. In fact, this is what's being done all the time. We study QCD and we say the pure gauge theory has confinement because we studied the Wilson loops, even though there are no quarks. And no quarks, the Wilson loop is the effect of probe quarks. In the toric code, there are electric and magnetic charge excitations, and they have statistics and this and that. And the low energy observer says, we don't need to think about them. It's enough to think of the universal behavior, which is a Z2 gauge theory in the continuum. And all the grading and all that comes about by studying the defects. Did this answer your question, Greg?
Yes, thank you very much.
So now I'd like to move forward and Higgs the system. So we discussed the matter system. So we just follow what we normally do in the quantum field theory course. Namely, we had matter fields, we had a scalar field phi, we had a gauge theory where the gauge parameter is like phi. Now we couple them together and we consider the Higgs system. And we would like to Higgs the U1 gauge theory down to Zn. So all we need to do is make phi carry charge n. So we write the following Lagrangian. B and E appear as Lagrange multiplier. There is a time kinetic term for phi in A0, and there is a spatial derivative term for phi in AXY. And the gauge symmetry of A was copied from the previous slide. And the gauge transformation of phi shifted by alpha, and the coefficient n here is correlated with the coefficient n here and the coefficient n here. And that guarantees that the U1 gauge theory is Higgs down to Zn. So this is a description of a Zn gauge theory. It does not have more degrees of freedom. It does not have any excitation. This is the absolute minimum for what would be a continuum Zn gauge theory of such a tensor gauge field. And another way to think about that, we already said that phi can be dualized by changing phi and phi into phi tilde. It's the same the same duality transformation we mentioned before. And then this Lagrangian can be written as n phi tilde EXY. EXY is the electric field. Phi tilde is a circle-valued field. I wrote the identification here. And this is what is normally called the BF description. This is B, in which in this case it has a single component. And this is F, which we have only the electric field, so we wrote it as EXY. And what is the spectrum? So we take this Lagrangian. How do we analyze the spectrum? There's various ways we can do that. A simple way is the following. The Lagrange multipliers B and E tells us that we can solve for A0 given D0 phi. We can solve for AXY given phi. So given phi, we can solve for A0 and AXY. This is the solution. So the ground state of the solutions is the space of all possible phi's modulo the gauge symmetry, which is this identification. So this space of fields is generated by precisely the function that we know and love, the function that appeared in this talk already several times in different incarnations. For every value of x0 and for every value of y0, we can put an integer modulo n, because if the integer is n, we can absorb it by our gauge transformation. So if we account for the common zero model, we study this function phi, the gauge transformations don't matter. We count the number of ground states of the system. And the number of ground states of the system is n of Zn, because we're describing the Zn theory, to the power Lx plus Ly minus 1. Minus 1 because we have to be careful about the zero model. Exactly the same answer is obtained in the lattice version of this system, where I never have to discuss delta functions, I never have to discuss 1 over a, etc. And here we found reproduced exactly the same answer using our continuum formalism. So we have this very large ground state degeneracy. This is all these states of zero energy, and there are no other states. So the spectrum of this theory is this number of zero energy state, period. This is the full spectrum. The lattice system also has some higher energy modes, higher energy states, but we don't have that. So we have what you can describe as a universal description, only the low energy spectrum.
Nati,
Yeah.
you can relate, I mean, this degeneracy is related to some, you have this Zn on with the dual Zn cross Zn. And
excellent question. So
this
this,
they are broken.
Yes.
This degeneracy is related to the breaking of
yes,
this.
yes to everything. The degeneracy is such that the Hilbert space, the entire Hilbert space with this number of states, is in the lowest representation of some algebra of operators, which reflect an exact global symmetry of this Lagrangian. And it's again one of these exotic symmetries or subsystem symmetries because the charges are supported on lines rather than on the whole plane. I'll soon give an analogy of a system that you know very well, and which is not as sophisticated as that, but it has some of the same elements. And so, in fact, one way to get that degeneracy is to just write the spectrum of operators of the theory and ask, how can we realize these operators in the Hilbert space? And this is the lowest dimensional representation. So let's discuss the defects a little bit. This is essentially the same as in the U1 system that we discussed earlier, except that the nth power of the defect is trivial. So we have fractons and we have these dipole linomes. And again, this reproduces what appears on the lattice. So let me make some general comments about this system. The system is gapped. It has only zero energy states. There are infinitely many. I already said that. They are local operators, e to the I phi tilde. They generate an electric Zn symmetry. This is to answer Shimon's question. There's an electric Zn symmetry, and these are the operators that the low energy observer sees that generate that symmetry. They are charged under a magnetic Zn symmetry. Now, if the short distance theory does not have the magnetic symmetry, like we are on the lattice, then this operator can appear in the continuum Lagrangian and destabilizes. So a condensed matter person would say that this operator is present and therefore the system is not robust. For a high energy physicist, we don't care about the lattice, we just have a continuum system and it has a symmetry, and therefore this operator is naturally tuned to zero. Oops, sorry. Yeah, so that's what I wanted to comment on the Zn gauge theory. And every system I discussed so far looked like a more sophisticated version of the same system in one dimension less that has the same features. So the phi system looked like a compact boson in 1+1 dimension with its momentum and winding symmetries and T-duality, and the U1 gauge theory was reminiscent of a U1 gauge theory in 1+1 dimension. And the same is true here. This system is reminiscent of a Zn gauge theory, one standard Zn gauge theory in 1+1 dimensions. So we can describe it using such a continuum Lagrangian, where we Higgs a U1. We can dualize phi to phi tilde and have a BF description of the Zn gauge theory. There are no bulk excitations. The Zn gauge theory in 1+1 dimension is characterized only by the holonomy around the circle. The holonomy has n different values, and correspondingly there are n states in the Hilbert space, these states. And we can also describe these n states as associated with quote-unquote the spontaneous breaking of a magnetic global Zn symmetry. The Zn gauge theory in 1+1 dimension can be thought of as a system that has n ground states related by the breaking, related by an ordinary Zn symmetry. And again, this system is not robust. A continuum person would say, I don't care. A lattice person would say that if we study a Zn gauge theory in 1+1 dimension, these n states are not going to be there because this operator will be present because the magnetic symmetry is not a symmetry on the lattice. So this is what I wanted to say about 2+1 dimensions. Most of the work we have done, most of the follow-up work we are doing now is really in 3+1 dimensions. And here it's very essentially the same thing, except that it's a little bit more tedious. There's a phi theory similar to what we did in 2+1 dimensions. except that it's dual to an exotic U1 gauge theory, which we call the A hat theory. The A theory that we discussed here, the analysis is very similar. There's a magnetic field and there are many new elements, but in the end, it's dual to a non-gauge theory phi tilde. Notice that again, the pattern, these systems in 3+1 dimensions are analogous to similar systems in 2+1 dimension, where a scalar field theory is dual to a gauge theory, or a gauge theory is dual to a non-gauge theory. This is common in 2+1 dimension, and the similarity actually goes further. And this is true here. And then we can combine the matter system and the gauge fields. We can combine phi and A in Higgs the U1 to Zn, or we can combine A tilde with A hat with phi hat in Higgs U1 to Zn, or we can dualize them and couple just A and A tilde. So this gives us 3 dual descriptions of Zn gauge theory in the continuum. And that turns out to be the long distance behavior of one of the most celebrated fractal models in the literature, known as the X-cube model of Vijay Hai and Fu. And unlike the 2+1 dimensional exotic gauge theory, this is robust in the sense that even for a lattice person, even for a condensed matter person, this system is completely stable. At long distances, there is no local operator that relates different ground states. So the system cannot be destroyed. So I brought it here just to say that using this formalism and being careful about what's a delta function and 1/a and 1/a squared. So there were a lot of details, but I did everything in the continuum and I tried to be as conservative as possible. At some points we had to break the rule a little bit, but that's what we did. Using that, we reproduce not only the results on the lattice of these models, but also the most interesting results of, not the most, but some of the most interesting results of the fractal literature. So to summarize, fractals exhibit interesting properties which seem incompatible with the framework of quantum field theory. I think there is no dispute about that. This is true. These fractal models exist. They exist on the lattice, but it's not clear how to fit them into continuum field theory. And that's what we try to do. We try to present a non-standard continuum quantum field theory, which had 3 ingredients, 3 elements that are non-standard. Invariant only under discrete rotations. That I wouldn't even, it's not common, but it's not uncommon. Many people study systems that are not invariant, not Lorentz invariant and not even rotation invariant. There were these exotic global symmetries and gauge symmetries, these subsystem symmetries. They generalized the notion of generalized global symmetries. We presented here an example of a system where it's a global symmetry. Then we gauged that and we found such a gauge theory. If we explored it further, we would have found that the gauge theory also has its own global symmetry and so forth. This is perhaps the most interesting aspect, that both the fields and the gauge transformation parameters could be discontinuous and even singular. There were some delta functions here and there. They were not as continuous as on the lattice, but they were more discontinuous than in the standard continuum theory. So this is really where the heart of the matter is in this paragraph, that we allow fields that are more discontinuous than in standard continuum quantum field theory. But once we allow that, we just followed our nose and tried to be as conservative as possible, and we found rules how to deal with these functions, what is allowed, what's not allowed, and we were guided by the lattice, and we managed to reproduce the lattice answers. So these continuum theories captured the universal properties of the lattice model. In fact, they were designed such that they do exactly that. They reproduce the long-distance physics, and in response to Greg's question, the properties of probe particles. The lattice system has some charged particles. The continuum system does not have that charged particle, but instead, a continuum person at low energies knows a lot about these charged particles because they can be probed as defects in the low energy theory. As much as this discussion answered questions, it leaves a lot of things unclear and a lot of things that can be done. The most urgent thing, I think, is to make the treatment of the discontinuous fields more precise. I don't have to come here and say this is 1/a, this is a, this is 1/a squared, etc. we had some rules how to deal with these functions, and these rules should come out of a precise mathematical statement. I do not know what these statements are. I consulted with some mathematicians to give me pointers, and also with some physicists to give me pointers, but so far it hasn't materialized. We had funny gauge fields, exotic gauge fields, and we had these twisted bundles where, again, we just followed our nose and tried to be standard, but it's completely clear to me that we need a better understanding of the geometry of these funny gauge fields. We worked in flat space with periodic boundary conditions, and it's really important to put this system on more complicated manifolds, curved space, maybe different identifications, etc., and maybe even more complicated topologies. People have tried to do that with a lattice system. The buzzword there is that we have to put the system on a foliated manifold, but it's all done with a lattice. Personally, I feel that when we go to put it on more complicated manifolds, it's better to have a good continuum description so that we don't need to put a lattice there. But that's my prejudice. I could be wrong about that. There are also easier questions. We'd like to, and that's what we have been doing with a whole bunch of collaborators, students, postdocs, and we'd like to repeat it to other non-lattice models. There are other lattice models that people study. There's a long list of them in the condensed matter literature. I feel that every one of them should be recast in that framework with either probably free field theory, perhaps with funny derivatives, and such that we can test all our rules about the functions, the gauge symmetries, the bundles, etc. And perhaps more interesting would be to find new models that either will be motivated by the continuum treatment or perhaps will not have a lattice version, but will exist in the continuum. So there's a lot that can be done. Thank you for staying here, and please stay healthy. Thank you. Thank you, Thomas.
Thank you. Thank you, Nadi. Are there questions?
I have a question.
The infinite degeneracy, it looks that if you start to calculate, let's say, some correlation function, two Wilson lines, you will get infinity. How you regularize?
Not in the Hamiltonian formalism. So
Well,
it's
you know, in the path
you're right. You're right.
Path integral.
Yeah, if you do the path integral with Euclidean boundary conditions, with a Euclidean space and you compactify time, Euclidean time, you'll get infinity from the ground state degeneracy.
Yeah.
So first of all, that was already true on the lattice. So it's not infinite on the lattice, but if you just take the exact lattice description and you take the continuum limit, you will get infinity. So this is, I don't know if it's a bug or a feature, but our goal here is to take known lattice models and recast them in continuum language. So if they exhibit the property of the lattice system, I would view that as a success rather than a problem with the construction. But now, it's a valid question. What about the partition function? The partition function is infinite. This is true, but if I compute the ratio of the partition function with some insertion of lines to the partition function without the insertion of lines, I believe this will be finite. This has not been done. Having said that, we did compute in the paper various correlation functions in Rn, R2 or R spaces R2 or spaces R3. So we looked at some 2-point functions of exponentials of phi, for example. And one has to be extremely careful how to compute it because of all these infinities. But in the end of the day, we landed on our feet. Namely, we found what has to be finite is finite, what has to be infinite is infinite, and what has to be infinite at order 1 over a, which is universal, the correlation function captured that answer with the correct coefficient. So this is a test that what we're doing is sensible. The way I view that is not, here is a new theory, and I have to defend the theory as being the correct theory of nature. That's not the game here. The game here is trying to break the rules a little bit. And the question is, can we get away with it in such a way that we reproduce what appears on the lattice? such that eventually we get more confidence in the way we do computations.
I have a question. Two questions, actually. What happens if you try to couple this theory in 2+1 to a standard, let's say phi cube theories or standard quantum field theories that we study and love? That's the first question. The second question is, in 3+1, I could imagine instead of using a scalar to construct this, I can use a vector. Is that thing consistent? Is it meaningful? Presumably, if one does that, you could obtain some higher form version of these symmetries in some way.
Yeah, so in fact, your second question is the answer to the first one. If you couple your system to a more garden variety field theory, you're going to break that elaborate momentum symmetry that I discussed. So this is a valid thing to do, but this is a different system. It does not have that fantastic global symmetry that triggered many of the phenomena that I discussed. Now, as far as the second question, you could ask, are there other examples? And in fact, yes. The way I would view it is that we start from a system that has some spatial symmetry, say the cubic group, but there are other subgroups of SO3 that we can impose as the global symmetry. And then the next step, so we pick a subgroup of SO3, that would be our global symmetry, a global space symmetry, and not in the internal symmetry. And then we put fields in representations of that. So you said that we can put fields in the vector of SO3. Well, the cubic group has an interesting two-dimensional representation, which is related to the two-index tensor of SO3. But it's two-dimensional. It's not a spinor. It's a two-dimensional representation of the cubic group. So you can put a scalar. It's not a scalar because you can put a boson in the two-dimensional representation. It's not a boson. It's not a scalar because a scalar is invariant under rotation, and this object is not invariant under rotation. So you can put such a system where a boson is in the two-dimensional representation of the cubic group. And this is precisely this theory, the theory that we call phi hat theory. The theory phi hat is a 3+1 dimensional field theory where the degree of freedom is in the two-dimensional representation of S4. And it has some momentum symmetries and winding symmetries, etc. And it turns out to be dual to the gauge theory, this tensor gauge theory that I discussed here, but in 2+1 dimension. So your question is on the right track. Just as we constructed this theory, there are many things, other things you can do and put fields in various representations and put all sorts of interactions. Yeah, there are many things that can be done. And we're busy doing some of them. We cannot do all of them.
Okay, related to this question, and also related to Thomas's question earlier, then presumably one could sort of start with a garden variety Lorentz invariant quantum field theory and consider some non-canonical sort of breaking of the Lorentz symmetry, some vev related to some specific vectors that you pick, which could, for example, pick out this specific symmetry as a subgroup and flow to this. Is there a meaningful way one could do that, or is that just completely hopeless?
Well, I'll give you this, since it's related to the previous question of Thomas, I'll give you essentially the same answer. We didn't try that, but here is one challenge. You already said that we could put the fields in funny representations of the cubic group. So here is an example. In this theory, we have a boson phi hat in the two-dimensional representation of the cubic group. And there is a cubic invariant Lagrangian for it. It will be quite challenging to find that out of an SO3 invariant theory. I'm not saying it's impossible, but I think it will not be straightforward.
Thank you.
But it's worth trying. I don't know.
I noticed that Greg has his hand raised. So, Greg.
Yeah, I was also wondering about infinities coming from this infinite ground state degeneracy. So at first glance, it looks like the quantum statistical mechanics is going to be ill-defined, as you said. But the question is, okay, if you factor out that infinite ground state degeneracy, do you think, is there anything known about the density of states? So if you look at one of these solvable lattice models, I think they're solvable because they're sums of commuting projectors.
Right.
So does anybody know about the
Okay, I do not know
density
the
of
answer to that.
excitations above the ground state?
Right. So I do not know if things know about the full spectrum of excitations. I doubt it, but I could be missing it. But the perspective here is that we only look at the ground states. So we're doing, we're looking for a low energy effective field theory. And low energy really means zero energy. So we focus in this talk, I focused only on the zero energy states. So that's really the system at very, very low temperature, right? Because we don't excite, our system in the end of the day. So if I look at any one of these examples, like here, for example, we have an infinite degeneracy, infinite in the continuum limit, but all we care about is the zero energy state. The continuum field theory does not capture the infinite number of states. Example, the toric code has an infinite number of states, and we can study its behavior at finite temperature and this and that. That is not going to be universal. Somebody else has a deformation of the toric code, and the answers will be different. What is universal is the behavior at low energies, which is a Z2 gauge theory, a continuum Z2 gauge theory. And that has a finite number of states. If you are on the torus, it has 4 states. And then you can do the thermodynamics of the 4 states. It's not going to be too exciting, but that's what it is. But I really emphasize that there are really kind of 2 orthogonal ways to proceed. One, keep the lattice and keep the non-universal high energy fields. Everything is going, so keep the lattice, now everything is finite, and you have a lot of non-universal stuff at high energies, and you get sensible partition functions. But it's not universal, and it does not capture only the low energy states. The other approach is focus only on the low energy states. So you're only interested in what happens at very low energies, and whatever you do will be universal. That's the good news. The bad news is that since we take the continuum limit, there's an infinite number of states. That could mess up some expressions. But this is the nature of the beast, right? What can we do? This system does have an infinite number of states.
Well, I'm wondering if you factor out the infinite number of ground states, you could still get well-defined
well,
answers.
if you work on the lattice,
partition functions, things like that.
Right, so if you work on the lattice, everything is finite. On the lattice, there's a finite dimensional Hilbert space, so there's a finite number of states. There's no infinity ever. And you can compute it on the lattice. I do not know whether this particular computation was done. But what is clear is that the answer you're going to get will not be universal. Namely, you can add all sorts of other terms on the lattice, and you're going to get different answers. So all of them might be interesting, but they're not universal. So if you want universal answers, you should focus only on low energies. And then I believe that what we have been doing is really unavoidable. That's what happens at low energies. Low energies meaning the lattice being denser and denser and going to low energies. The surprising thing about these systems, even before we started, was that they have an infinite ground state degeneracy in the continuum. That's one of the main features of these models. So if the continuum theory produces that, I think it's a success. It's not a failure, because that was the goal. The goal was to produce a continuum field theory that has exactly the same infinity.
Let's see, I noticed that Thomas has his hand raised, so Thomas?
Yeah, I had one more question, just sort of an intuitive question, I guess, which is that in your models, you have this dimensional correspondence between an exotic theory in one dimension and a more standard theory in one dimension lower. And I was wondering if this is an accident of the models that you looked at, or there's some intuition for why this should happen or had to happen.
Okay, Okay. So first of all, by now we have examples where the analogous thing is the exotic theory in 3+1 dimensions is analogous to a standard theory in 1+1. So it's going 2 dimensions down. I believe it's related to the fact that we had 2 derivatives. So when we had dx dy, these 2 in the number, we had 2 derivatives instead of 1. I think this is what bumped us up 1 in dimensions. The other example has 3 derivatives, and it bumps us up 2 up in dimensions. At the moment, maybe one of my collaborators, if he's online here, can chip in. My understanding at the moment is that we're in a very, very exploratory stage. I'm not willing to make any blanket statement that something is always true in all models, because so far any new model that we look at has its own peculiarities and its own features. So in that sense, I do not know, but maybe if one of my collaborators on the line and thinks differently, I'll be happy to be corrected.
Let's see, there's a question from Ali.
Hi. So this is a question in the line of trying to get new fractonic models from the continuum limit. So the first example that you did was sigma model into a circle, except that there is now, instead of the usual Lorentz symmetry, we have a subgroup and some other properties. Could we try to generalize it by studying sigma model into other manifolds, for example, like a sphere, and try to write down Lagrangian of those theories and analyze those and their properties?
Yeah, you can. We haven't done it. It can be generalized in many different ways. This is one of them. I would stick at this stage of the game, I would stick to free field theories. And the theory to the sphere with a map to the sphere is not free.
Yeah.
It's not quadratic in the fields. There are lots and lots of possibility just with free fields, just because we can have different representations for the fields, representations that we're not always familiar. First of all, we can have different subgroups of SO3. Then every one of them has its own representations. And we can have several different representations. We can let them couple to each other, and we can sprinkle the derivatives in various ways. So there are many options already with free fields. And we haven't even introduced fermions. We had introduced fermions, it's a whole new set of complications. So it's very preliminary, but at least I see a systematic way to proceed. So adding interactions, I think, is an interesting thing to do, but I feel that this should be next down the road. But again, I view that as a step forward, because if you look at the lattice literature, they come up with examples, you know, this spin times that spin times that spin, kind of various combinations, and they do interesting things or they don't. Here we have a machine that produces examples, namely picks a S4, this cubic group, write fields in its representation. There's a finite number of representations, put the derivatives, there's a finite number of ways to do that. The theory is free, so the analysis is straightforward because the theory is free, and see what you get. So in that sense, it's more systematic and more easy and easier. But I feel that adding interactions, well, first of all, it's clearly interesting, but I don't think it will be easy. But it's worth exploring.
Another question would be that the Lagrangians that we're writing down, they should be invariant under, under the rotational subgroup that we have. Are there more than one possibilities? The same set of fields, can we write down more than one possibilities?
Yes, so there are examples where you can add terms. And so let me make your question broader and answer that in the broader question. The first question is, are our Lagrangians natural in the following sense? We impose some subgroup of the rotation group. We impose some exotic symmetry. Did we write all the terms that are allowed by the symmetry? And the answer is yes, we were very careful to do that. Then you could ask another question. Let's not impose the global symmetry, only the subgroup of SO3. And write with a given set of fields, we limit ourselves to 2 fields, and write terms with derivatives. Now we can write various different terms, and they will have different global symmetry. So we can say that we want the S4 symmetry, the same theory we discussed, but we don't like this momentum symmetry. We just want ordinary momentum symmetry. Then we just write a free field theory, dx5 quantity square plus dy5 quantity square. And then we realize that this system actually has the full SO2 symmetry. In 2 plus 1 dimensional, SO3 in 3 plus 1 dimensional. Or you could write big phi in some representation, some other representation, and put the derivatives differently, and then we'll get another global symmetry. Make sure that you have all the terms that respect that global symmetry and start from there. But there's still many things to die. I hope it answered your question.
Yeah, thank you.
I have one more question. So going back to the comparison of the 1 plus 1 and the 2 plus 1, if you compactify the 2 plus 1 down, is it obvious that you recover all of the features that fits this sort of analogy?
If I compactify what?
If you take the construction that you have with the 2xy derivative, and you take the y direction as a compact, and then you reduce, then naively that might look like something which is Lorentzian in 1 plus 1. What happens to these new global symmetries? Does this make the analogy of the 1 plus 1 and the 2 plus 1 clearer or not?
Okay, so we can just do it in real time, and you will see that it will be quite simple. So we take this system. If we reduce on the y direction, then
yes,
this term is gone.
Yes.
And then you have just a theory in x, which is d05 squared, which is essentially the modes that depend on x that I discussed earlier. This is not the theory in 1 plus 1 dimensions that has T duality.
But maybe if you keep some harmonics along y.
Well, I don't know what to do. We tried various
the
things.
phi direction, you might end up something that's left over.
There might be a way to do that. We tried various tricks because the similarity between these systems that I discussed here in 2 plus 1 and more standard theories in 1 plus 1 really begs for an explanation. And we couldn't find anything that, we just manipulate the Lagrangian and gives that. This is also related to the question of whether it's always true. I do not know whether it's always true. Maybe it is, maybe not.
Thank you.
Are there any other questions? Okay, if not, let's thank Nati again.
Thank you.
And I'll send in chat the webpage for the seminar series. In 2 weeks, we'll have Atish Davokar.
Great.
Thank you, Nati.